Okay. So Assalamualaikum. For today, our group want present about control system assignment, which is DC motor. But before we start, let me introduce myself. My name is Yassin bin Muhammad Azmi. My number ID is 511-0212-3077.
My name is Ahmed Abdullah bin Muhammad Helmi. My student ID is 511-023-23-026.
So my name is Anas bin Yassin, and my student ID is 5110-2323-016.
And my name is Muhammad Dinur Hakim bin Shariman. My ID's number is 51102323 023. Okay, thank you.
So we go through into introduction. So DC motor is a fundamental component in control system, providing rotation motion that can be converted into translation motion for various applications. By analyzing its electrical circuit and mechanical dynamic, we can develop simulating models to understand its behavior and optimize performance through control technique. This presentation delves into closed-loop control system designed using MATLAB, modeling, and simulation, exploring key parameters such to torque, inertia, resistance, and electromotive force constants. A properly tuned PID controller is essential to achieving desired system performance in terms of stability, accuracy, and responsiveness. So this is the first task, which is we need to design a PID position controller to meet the following criteria. And the time response and frequency response analysis can be done using MATLAB or Simulink. So next slide. So this is our circuit design, and actually this Simulink model represent a closed loop PID control system for a DC motor designed to regulate the position of the motor shaft based on a reference input. So let's walk through the system step by step. So first one, on the left, we begin with a step input block. This will represent the desired position and that we want the motor to achieve. So next, this signal is passed into a sum block where it is compared with the actual output position from the feedback loop. And the output of this block is the error signal, the difference between the desired and actual position. So next, the error is the error is fed into a PID controller block. The controller applies proportional, integral, and derivative control to reduce the error over time by adjusting the motor input voltage accordingly. And since we are interested in position, not just speed, the output speed is passed through an integrator block, which effectively converts speed into position over time. And finally, the max output is sent to a scope block. This allow us to view the system response. And in summary, this model demonstrates how a PID controller can be used to automatically adjust the voltage applied to a DC motor and to achieve precise and stable position control. So next slide. So this is our subsystem. For this, Simulink model represent the physical behavior of a DC motor based on its electrical and mechanical dynamics. So first one on the upper path, we see the electrical model, which is the voltage input represent the electrical power applied to the motor. And the voltage is subtract from the back EMF, which is electromotive force, which is modeled using the gain block label. And next is the current then flow into the lower path, the mechanical model of the motor. And next, the speed is also fed back into the upper branch, where it is multiplied by KE to generate the back EMF. And the final output of the model is the angular speed of the motor shaft labeled as speed. So this model simulates the true behavior of a DC motor by solving its governing differential equation in real time. And this model also can be used inside a control system like the PID system to simulate how the motor responds under different input voltage and feedback conditions. So that's all for the subsystem. And next.
Very well. Now I will explain the results for task 1. As we can see, the rise time is 0.531. The settling time is 6.04 seconds. The overshoot is 1.24%. The gain margin is 41.4 dB. The phase margin is 63.9 degrees. The closed loop stability is stable. The solid blue line shows a smoother and more stable system behavior compared to the dashed line. And the overshoot is very low, and the system quickly reaches the desired set point without oscillations. The system is robust and reacts well with disturbances due to the high gain and phase margins. In task 1, a PID controller was successfully designed and implemented in Simulink to control the position of the DC motor. The goal was to meet the specific time domain performance and requirements, including a percent overshoot of less than 20%, a rise time of less than 2 seconds, a settling time of under 10 seconds, and a minimal steady state error. Using MATLAB PID tuner, the controller parameters KP, KI, and KD were adjusted for PID. And the simulation results confirmed that all criteria were met. The tuned system achieved a rise time of 0.531, just okay, 0.531, which is under 2 seconds, and a overshoot of 1.24, which is under the 20% requirement, which is less than 20%, which is the requirement, and a stable response with good accuracy. This task demonstrates the effectiveness of PID controller in shaping the dynamic response of a system and emphasize the importance of proper tuning to achieve the desired performance. Okay, next slide.
So this the second task for this assignment, and we need to find the closed loop transfer function of the output speed to input voltage, and we are required to do it manually and using MATLAB. And the objective of analyzing the system using time response and frequency response, which is what diagram. So next slide. So this is the circuit design for the task 2. And actually this simulating model represent the complete physical behavior of a DC motor by mathematically simulating both the electrical and mechanical systems. So let's walk through it by step. So first one is the electrical subsystem, which is upper part of this circuit diagram. The model starts with a voltage source input. This is the electrical energy supplied to the motor. And the voltage fits into a sum block where the back electromotive force is subtract and back EMF is calculated using the motor's angular speed multiplied by the constant Ke. And next is the mechanical subsystem, which is the lower part. The armature current is multiplied by the torque constant Kt to generate the mechanical torque. This torque drives the rotor and is applied to a system that models inertia and damping. And the result of this mechanical effect is the output, the angular velocity of the rotor, and which is labeled as speed. And last is the feedback loop. The angular speed is fed back into the top portion to compute back EMF using the constant key. And overall, this Simulink model capture the real behavior of a DC motor using first principle equation. It's essential for validating the motor's performance before applying any control, such as PID. And this model is often used inside larger control system for precise simulation and analysis. And that's all for the circuit design for task 2. And we go to the board diagram.
For the block diagram, we can see that the phase starts near 0 degrees and drops down to negative 180 degrees, which is expected for the second order system. In task 2, the closed loop transfer function of DC motor system was derived both manually and using MATLAB. Using MATLAB. The mathematical expressions was obtained by applying system equations and the feedback control principle. Using MATLAB tools, the transfer function was simulated, and its frequency response was analyzed using a blot plot. The results showed that the system had a gain margin of 41.4 dB and a phase margin of 63.9 from the previous PID, indicating a strong stability and robustness. This task highlighted the significance of analyzing control system in the frequency domain and evaluate their stability margins and their performance under varying conditions. It also reinforced the importance of transfer function modeling in understanding the behavior of closed-loop systems. The blot plot confirms that the PID control system is stable and robust. The gain and phase margin meet the desired requirement, and the system will tolerate reasonable parameter variation or disturbance without becoming unstable. That's all for this task.
So the fundamental use of PDI controller. A PDI controller is a proportional integral derivative controller. It's one of the most widely used control strategies in engineering and industry. It is used to automatically adjust the output of the system to achieve a desired set point in the present percent of disturbance and uncertainties. Next. What does a PID controller do? A PID controller continuously calculate an error value as the difference between a desired set point and a measured process variable. It applies a correction based on the term. So the first one is proportional. P. React to the current error. The large the error, the stronger the control action. Help reduce the rise time. The second one is integral. React to the accumulated past error, eliminate steady state error, ensure the output reach the stage at the set point, and increases system accuracy over time. And the last one is derivative D. React to the rate of return of the error, predict future error based on its trend, help reduce overshoot, and improve stability. The next one. Why is PID control important? Stability help maintain the system in the controlled and predictable state. The second one is accuracy. Ensure the output closely matches the desired set point. Speed. Enable faster response to change or disturbance. The last one is simplicity. Easy to implement and tune for many types of system like motor, temperature control, and more. And all right. So the next, Mike.
So for our conclusion for this project, we successfully designed and analyzed a PID controller for a DC motor system using MATLAB and Simulink. The main objective was to ensure that the motor's position control met specific performance criteria, including minimum overshoot, fast rise time, quick setting, and strong system stability. Through careful modeling of the DC motor based on its its physical parameters, and by applying control system principle, a realistic and accurate simulation was achieved in Simulink. The PID controller was tuned using MATLAB PID tune, and the results show that the system achieved a rise time of 0.531 seconds and overshoot of only 1.24% and a stable steady state response, all within the desired limits. Additionally, frequency domain analyze using the bot plot confirm the system robustness with a gain margin of 41.4 decibel and a phase margin is 63.9, indicating that the closed loop system could tolerate disturbance and ascertain effectively. This project highlights the importance of using closed loop control system in practical application and demonstrate how PID tuning can be used to improve the dynamic performance of electromechanical system. The combined use of time domain simulation and frequency domain analysis provide a comprehensive understanding of the system behavior, ensuring that the controller system was both effective and reliable. So I think that's all from our group. So thank you.
Thank you.